Hi, this is Nathan Smith. In this tutorial, we're going to learn how to use the Neo4j GraphDataScience library and the Emblaze plugin for JupyterHub to understand graph embeddings. The code for this tutorial is available on GitHub, and there's an accompanying blog post on Medium, and the links to those resources are in the description below. So to begin, you'll want to download this Jupyter notebook and open it in JupyterHub. And then if you haven't installed the Neo4j GraphDataScience library for Python, that is what's going to happen in this first cell, and then the next cell is going to install Emblaze for me. I've already installed those, so I'm going to skip those cells for right now. And I can go right here and import the Python libraries that I'm going to need for the tutorial. And then the next step that we need to do before running this notebook is setting up a free Neo4j sandbox. So I've signed in at sandbox.neo4j.com, and then I'm going to say that I want a new project, and I'm going to select the GraphDataScience project and tell it to create. So this is going to set up a free sandbox that will be available to me for about 3 days. I also have the option to extend it for a little farther. And this comes preloaded with the Neo4j GraphDataScience library. It also has a data set that includes airports and some geographic information about the airports, what country they're in, what continent they're on, and also the routes that are between the airports and the distances of those routes. So that's all been set up for me now. But the next thing I did want to capture while I was still there in Sandbox was to look at the connection details. I need to gather this password and this bolt URL. I'm going to start with the bolt URL and copy that to the clipboard. And then when I come back here to the notebook, I'm going to replace the bolt URL, and I'm going to replace the password. Very good. So that's done. And this has now set up my GraphDataScience connection. This is a new Python client for Neo4j GraphDataScience that has just come out as part of the GraphDataScience 2.0 release. So if you've worked with GraphDataScience and Python before, the syntax might look a little bit different, but I think they've done a really good job of making it intuitive how to work with this new client. And the syntax actually looks a lot more like just working in Neo4j browser than it's looked like in the past. So I'm really happy about the progress that's being made on that front. So the next thing that I want to do is look at this has route relationships between the airports, and they include a property that's called distance. And what I'd like to do is create a new property called weight. And what I would like is for the weight property to have high values when the distance between two airports is low. And so this little bit of Cypher is just finding all of the airport pairs that have a route connecting them between the two. It's collecting up all those routes and finding the maximum distance between two airports. And then for each route, it's setting a new property called weight, which is the max distance plus 1 minus the route distance. And so what that's going to do is for airports that are close together, they're going to end up with a higher weight, and airports that are farther apart will end up with a lower rate. And this is just a simple linear transformation to achieve that. You could do something more complicated if you want to. One idea might be to take the route distance and raise it to a negative exponent, and that would be another way to cause the airports that are far apart to have a low weight and the airports that are closer together to have a higher weight. But for us, we're just going to keep it simple and do a simple linear transformation. And then next, what we're going to do is create an in-memory graph in Neo4j. We're going to project this graph to have all of the airports in it and all of the has route relationships, but we're going to treat those has route relationships as undirected. And in cases where there's more than one relationship between a pair of airports, we are going to aggregate them together into a single undirected relationship, and we will take the maximum property values associated. And for the relationships, we're going to bring in that weight property. So I will run this. And then this is going to return the graph object. and it's also going to return the results of that projection. So let's take a look at the results. It looks like it went just fine. I ended up with 3,503 nodes, 49,476 relationships. And let's just make sure that we got that has route relationships weight property to come through. And when I list the relationship properties associated with has route, I see that weight is there. So that's promising. It looks like everything worked the way that it should. Now, one of the things that I like to do as part of my exploratory data analysis step when I'm working with graphs is to run the weakly connected components algorithm. That's what WCC stands for, weakly connected components. And that lets me know if there are sets of nodes within the graph that are reachable according to the paths that are within the graph. And so when I run this, it runs quickly, and then I'm going to look at that component distribution, and I can see that I have one giant component that has 3,292 nodes in it. So the big majority of the nodes in the graph are part of this giant component, but then I also have several nodes that are part of small components. Looks like most of them have just a single node involved, and I suspect that those isolated nodes are probably general aviation airports that aren't reachable by commercial airline routes. And those airports are not really that interesting to me for the demonstration that we're doing today. So what I'm going to do is call that WCC algorithm again, but this time in mutate mode. And in mutate mode, that will add a new property onto each node called component ID. And this is only going to happen in the in-memory graph. It's not happening on the graph that's persisted on disk. So we'll run it in mutate mode, and that's going to modify the in-memory graph. And then I'm going to write that node property out from the in-memory graph back onto the persisted graph on disk, and I'm going to call it component ID in the on-disk graph as well. So there we go. That has happened. Now I have a new property on my graph on disk as well. And what I want to do next is check to get the component ID that's associated with that giant component. So this little bit of Cypher is going to match all the airports and return their component IDs and the number of nodes associated with that component ID. We're going to order it by the count of nodes, and we're going to do that in descending order and just take the very first one, the top one. So our result is that component ID 0 is the one that's associated with that giant component with 3,292 nodes. So the next step that I'm going to do is to create a subgraph. So it's going to start from our groutes graph that we had, but we're going to filter it to show only those nodes where the component ID is 0, and I'm going to keep all of the relationships. And this new graph is going to get a name in memory called connected airports. So we'll run this step to create that projected subgraph. And then just to make sure that everything worked the way that we expected, I'm going to, for this connected airports object, just get its node count, 3,292. Oh good, that's exactly what I expected. So this is the graph that we're going to work with for the rest of our demo. So now that we have that data exploration and data prep out of the way, we're going to move on to training graph embeddings. And we're going to use a function or an algorithm called FastRP. FastRP is an abbreviation for fast random projection. And it's a good node embedding algorithm for us to use in this case because, as the name suggests, it's very fast. So for a smaller environment like we have in our sandbox, this algorithm works very well. And FastRP is also very good at giving us a sense of the neighborhood around each node, and that's really what we're looking for in this case, is something that will tell me not only where does this node sit, but who are its neighbors and maybe the second and third degree neighbors on beyond that. So this function that we're creating, train FastRP, will accept a graph and then a configuration. And we're going to pass the graph into the FastRP mutate function from GDS. And we're going to have a few parameters that are consistent for every graph or every configuration that we're dealing with. And then we're also going to have some variables that we're going to change. And we're going to be looking at when I change these variables in the configuration, how does the output get impacted? So the things that we're going to keep consistent are we're going to pass the same graph every time. We're going to have the same embedding dimension. This is the length of the vector that gets created. So by setting the embedding dimension equals 64, every vector is going to have 64 different numbers in it. This is something else that you could experiment with in Tune. Because our data set isn't all that big, 64 is going to be a decent number for us to work with. For that embedding dimension, but if we had a much larger data set, I might bump this up to 256 or even more for that embedding dimension value, but 64 is going to work fine for all of ours right now. And then the random seed, as the name fast random projection suggests, there is some stochastic processes that are happening as part of this algorithm. By setting the random seed equals 45, that gives me consistency if I run the algorithm more than once. 45 is just a number I picked out off the top of my head. You can use whatever number you would like there. And now let's look at the different configurations that we're going to pass through to that function. All of these configurations have values set for this iteration weights property. You can see that there's different values that we're choosing for the iteration weights. The iteration weights controls how many times the FastRP algorithm runs, how many times it iterates, and then the number represents the weight that's associated with that iteration of the algorithm. Every iteration of the algorithm steps farther away from the source node that's having the embedding calculated to its neighbors that are farther and farther away. So the first value here is the impact that the first degree neighbor is going to have, and then the next number is the impact that the second degree neighbor is going to have. So this first configuration that we're looking at is going to just deal with the very next door neighbors, the first degree neighbors, and then the second degree neighbors. And so we're going to call this particular output the shallow unweighted version of our embedding. The next one is going to have a 1 in the position for the second degree neighbors and the third degree neighbors, and it's got a 0 for the first degree neighbors, and that might seem kind of weird, but since we're including the second degree neighbors and the third degree neighbors in there, the first degree neighbors are going to get picked up. If I step out from this first degree neighbor by 2 steps, and then I step back by 3 steps, then I'm going to end up with influence from this first degree neighbor as well. So that's why it's still going to get counted even though it's got a 0 for that pass of the embedding. So that's our medium unweighted, and then I've got a deep unweighted where I'm going to allow the algorithm to go 4 steps out. So I've got 4 numbers in that list, and that's going to give me my deep unweighted version of the embeddings. And then I've got another set of embeddings that have the exact same iteration weight properties, but they also include a relationship weight property. And so these are going to also consider the weight or the strength of those relationships between the nodes as it's calculating their influence at each iteration of the graph. So altogether, we've got 6 different versions of the configuration that we're going to be considering. And so now I'm going to actually calculate those embeddings based on all those 6 different configurations. And these embeddings are going to be stored in the in-memory graph. And so wow, that was fast. We can look and see the results. It was just a matter of milliseconds to compute all those, and it's got the same node count for everyone. The configuration is there. So that seems like it went very smoothly. So the next thing that we're going to do is run a Cypher query that will stream back those node properties from the graph. And so I'm going to get back the shallow unweighted, medium unweighted, deep unweighted, shallow weighted, medium weighted, and deep weighted values of those embeddings. I'm also going to get back the airport name, the airport code, and the continent that the airport's on. And then I decided to sample just the top 900 airports based on the number of routes that they have. And I did that because Emblaze is going to perform better with a data set that's not so big, and also because some of those airports with very few routes connected to them, I just don't know enough about geography and aviation to even recognize where they are in the world, but by taking the top 900, hopefully those will be airports that are a little bit more familiar to me as place names. So I look at the results and I can see that I have the airport name, the code, the continent, and then I have these 6 embedding columns. And these embedding columns are not really human readable. They're just a list of numbers. And this is where Emblaze is really going to help us unpack what these embedding results mean. So next I've got a function here that will take a column out of this data frame and turn it into an Emblaze embedding. So it's going to have the position, that means the coordinates of the node in that 64-dimensional space. It's also going to have a color for each node, and we're going to color these nodes by the continent. That way we can see if nodes that are on the same continent tend to group together in the embedding space. We're going to calculate the 10 nearest neighbors for each node, and then we're going to give the whole entire embedding a label that matches the column name. So it's going to be, these 6 column names up here are going to be the labels that get associated with the embeddings. Then we're going to tell Emblaze to actually compute the neighbors, and then this project step is telling Emblaze that we want it to use the UMAP algorithm, which comes standard. You actually have a few different choices of projection algorithms. We're just going to take the default UMAP algorithm to take that 64-dimensional vector and project it into 2-dimensional space so that we can look at it in a 2-dimensional view on the layout. So that will help us visualize it. So now I have this list of embeddings, and I'm going to turn those into an Emblaze embedding set. And then I'm going to create text thumbnails with the airport's name and the airport code. And those thumbnails are just going to show up when I hover over points in the visualization so that I can see the name and the airport code in the visualization. And finally, I'm going to create that Emblaze viewer. And now that I've created it, I just call it, and that widget shows up here in JupyterLab. So the first thing that I notice when I look at this is that I have my little thumbnail panel along the left side here with each of my different embeddings, my shallow unweighted, medium weighted, deep unweighted. And you'll notice that in addition to the thumbnails, there's this little color-coded bar along the side. And I already can see something interesting by looking at the colors of those bars, because Emblaze is going to try to put similar colors on the embeddings that put the nodes into similar positions in the embedded vector space. So I can see that the shallow unweighted has kind of a greenish color, and the shallow weighted has also kind of a greenish color. Medium unweighted has a lavender color that's not so different from the medium weighted blue. And then the deep unweighted is on the reddish-orange spectrum, and so is the deep weighted. So what that suggests to me is that the iteration weights parameter that these embeddings have in common, the unweighted one and the weighted one that are both shallow, have the same iteration weights, but a different weight property. It looks like the iteration weights are more influential in where the nodes end up than whether or not we chose to use the weight property or not. So that's an interesting insight that we can gain right off the bat in terms of which of the parameters was influencing the way that the nodes end up in the embedding space. So right now I have the shallow unweighted embedding highlighted. If I click on the next one down here, you can see that Emblaze is drawing lines to show me the direction that the nodes that change position most pronouncedly are going to move. And so that's interesting right off the bat. When I click at this, I can see it looks like the European airports are maybe moving a little bit farther away from the African airports in this, from when I go from shallow unweighted to medium unweighted. I'm going to double click here now, and it actually does the animation, and I can see how they moved through. The other thing that I can do is when I click on this, oops, I'm zooming, I didn't mean to zoom. I meant to scroll because I wanted to show, well actually I'll just expand this to make it a little bigger, yeah. When I scroll, I can pause that animation at any point along the way if that's helpful to see and kind of determine what's moving where and how things are interacting along the course here. So that's a great way to be able to compare the different embeddings as a whole. It might be interesting for me also to look at an individual airport. So I'm going to search here for MCI, which is the airport code for Kansas City International Airport, which is my home airport. And I can see when I search for it, it zooms in on the embedding, and then it also shows me the list of the 10 most similar airports in that embedding space. And if I hover over these, it will highlight where they are on the picture. If I click on one of them, it will make that the selected airport for me to look at. So I'm going to come back to Kansas City here. Another interesting thing I can do, right now I'm looking at the medium unweighted, and if I click over here on the medium weighted for the comparison, now this is going to give me the list of what changes. It looks like between those two embeddings, Kansas City has the exact same top 10 neighbors. Let's try a different one. Oh, when I switch from medium unweighted to deep unweighted, Kansas City does get some different airports. Let's look and see. It looks like it's going to lose Oklahoma City, Tulsa, and Austin as neighbors, and it's going to gain Gerald R. Ford, Raleigh-Durham, and Cincinnati. So that's kind of interesting because these are airports, the ones that it's losing from the medium unweighted are airports that are more in the center part of the United States, or Texas, Oklahoma, central time zone. The airports that it's gaining are a little bit farther away geographically. These are, this is Michigan, North Carolina, so we're moving into the eastern time zone, and that's really what we would expect, that the medium was looking at their closer neighbors, and then this is looking at neighbors that are a little bit farther away into the graph. So that's an interesting explanation of what these different parameters are doing for us. So I'm going to hit this reset button to zoom back out and look at the graph as a whole, and I'm going to choose the medium unweighted, and then I'm going to compare it to the medium unweighted. And then if I click on this suggested button over here, it's going to calculate a list of airports, groups of airports that have interesting changes from one embedding to the other. So here I've got a list of airports that has Melbourne, Canberra. I'm going to load this selection and see. It looks like these are airports in Australia or Christchurch, New Zealand. And this one is in New Caledonia. So I've got airports that are in Australia, and as I scroll down the list here, I can see what changes when I go from the medium unweighted to the medium weighted. And here it gives me a list of common changes, and it looks like a very common change is when I go from the unweighted to a weighted approach, that I'm picking up the Townsville Airport. And that is an airport in Queensland, which is geographically close to these other airports. And when I switch to the weighted, I'm losing some of these other airports like Bali and Fiji. And those airports are geographically a little bit farther away than Townsville. But when I looked at the graph, I saw that they had more two-hop connections between Bali and Fiji and the airports on the list than Townsville did. And so that's, again, helping me get a handle on what's the difference between looking at this as a weighted graph versus an unweighted graph when I calculate the embeddings. I hope that this tutorial gives you a sense of what embeddings are and how the combination of Neo4j with the Emblaze plugin can be a really nice tool set for interpreting and unpacking this powerful technology. And I hope to see your comments on the blog and see your progress with this technology in the future. Thank you.